Welcome to the lecture series on numerical methods, a finite difference approach. And in this method already we have discussed this explicit scheme, implicit scheme and Crank-Nicolson's method, that is a semi-implicit approach, and their stability and convergence analysis. And in the present lecture we will discuss about this boundary condition treatment. That means if suppose derivative boundary condition in the form of like either in the form of a Newman boundary condition or in the Dirichlet boundary condition or in the form of like mixed derivative conditions, if it is just provided, how we can just deal this boundary conditions, that we will just discuss. So when we will just go for this like Dirichlet condition, especially in that sense, this boundary conditions are prescribed along the boundary in the form of variable. So it is easy to handle there itself. If the boundary conditions are given in the form of like Newman's condition or in the forms of mixed derivative conditions, then it is difficult to handle sometimes. Suppose the prescribed boundary conditions are given in a mixed derivative condition, and mixed derivative condition especially we have just discussed that one in the form of like alpha 0 del u by del x plus beta 0 u, this equals to gamma 0 at x equals to x 0. Since we will have these boundaries, that is in the sense like so at x equals to 0 you should have to prescribe a value, and x equals to L we should have to prescribe a value. Since along this boundary this will be supplied by this initial condition. And if at x equals to 0 this mixed derivative condition, that is just represented in the form of like a mixed derivative term here, that is alpha 0 del u by del x plus beta 0 u equals to gamma 0, and along the last boundary it is also mentioned this boundary condition in the form of like alpha n del u by del x plus beta n u, this equals to gamma n at x equals to x n. Since our domain starts from x equals to x naught to x equals to x n here. And especially if you will just consider these coefficients, that is as alpha 0, beta 0 and alpha and beta n all are constants. Sometimes it may be prescribed 0 values also there, and this gamma 0 and gamma n, they are also constants here, and sometimes they are also given as 0 values. Since usually if the normal derivative condition is 0 suppose, then you can just write del u by del n equals to 0 along the boundaries. So whenever we will have these boundary conditions in a derivative form or in mixed derivative form, then two ways we can just find the solution for this internal discretized equations, or we can just use directly this boundaries discretization scheme there itself to get the solutions there. So these methods are especially you can just use either this forward difference or backward difference method or the central difference approximations. So if you just go for this forward and backward difference approximation here at suppose the beginning of the point, like along the first boundary, suppose at x equals to x naught suppose. So if you just replace this derivative, that derivative condition especially it is just written as alpha 0 del u by del x plus beta 0 u, this equals to gamma 0 there. So if we will use this like the forward difference approximation here, so we can just write this one as alpha 0 u1 j plus 1 minus u0 j plus 1 by delta x plus beta 0 u0 j plus 1, this equals to gamma 0. Since along this boundary if you will just see here, so I is starting as a 0 here, and the last boundary you will have I equals to n there. So I equals to 0 means we can just start this boundary like your condition as I equals to 0 and I equals to 1. So especially at I equals to 1 you have to compute these values, and this is also given in the derivative condition here. And if you just move forward to one step there, then we can just find at each of these time step levels. So that's why we have just written this one as j plus 1th level. So at each of these time step levels we can just use this formula to get this discretized scheme there. So that's why if you just write this one in the form of like alpha 0 u1 j plus 1 minus u0 j plus 1 by delta x plus beta 0 u0 j plus 1, this equals to gamma 0 here, then we can just separate this boundary value for u as in the form of like alpha 0 u1 j plus 1 minus gamma 0 delta x divided by alpha 0 minus beta 0 delta x here. Since u0 j plus 1, it is just taken common from both these terms here. And especially you will have a previous iterated value or some initial conditions it has been provided for inside the domain here, and from that initial values of this computed domain, this boundary can take this value and it can be updated in each of these iteration levels. Similarly, to find suppose at the last boundary value, that is at un j plus 1 here at each of these time levels, then we can just define this derivative in a backward sense, since we do not have any other domain afterwards there. So, we can just use this previous or backward step to get the solution there. So, if you just use a backward step here, then we can just write this point as n minus 1 point there for j plus 1th level. So, this discretized scheme can be written as in the form of like alpha n un j plus 1 minus un minus 1 j plus 1 by delta x plus beta n un j plus 1, this equals to gamma n. Especially people are using like at the inlet or along the first boundary this forward marching, and at the last boundary or at the outlet especially it is just used as the backward difference approach. And if you just go for central difference approximation here, then we have to consider some fictitious boundary there, since especially for this we need like 3 cells at the boundary. If you just treat, since if you will just consider like first boundary x equals to x naught here, for the central difference scheme we need like this inside point 1 and outside point 1, but there is no existence of a domain there. So, that is why this is called your fictitious domain here. So, or artificially you can just consider this domain there itself, and you can just consider that point as the point. So, for this you have to extend the domain like in the left or in the right if this condition is asked, or if it is asked to use the central difference approximation at the first boundary or at the last boundary. So, you have to extend these boundaries. So, if you just extend this boundary, since x0 is the last point here, so the previous point it can be signified as x of minus 1, and the immediate next point of this last boundary it can be written in the form of xn plus 1 here. And at x equals to x0, if you just approximate this derivative by the central difference approximation here, we can just write this one as u of 1 j minus u of minus 1 j here. This divided by 2 of delta x into alpha 0 plus beta 0 u 0 j, this equals to gamma 0. Since 0 is the boundary condition we are just considering here for this initial step, which gives since this u of minus 1, this is not known to us, and fictitiously we have just considered this boundary here. We can just write this one as u of minus 1 j, this equals to u1 j plus 2 delta x by alpha 0 beta 0 u 0 j minus gamma of 0 here. And similarly, if you will just consider at j plus 1th level here, then we can just write this one as u of minus 1 j plus 1, this equals to u1 j plus 1 plus 2 delta x by alpha 0 into beta 0 u 0 j plus 1 minus gamma 0 here. So, if you will just go for the central difference approximation here, so consider suppose u of minus 1 j, which is known by suppose this previous equation, if you will just see, that is in the form of u of minus 1 j, this equals to u1 j plus 2 delta x by alpha 0 beta 0 u 0 j minus gamma 0 here. So, then we can just compute u of minus 1 j, and in the same way we can just approximate this boundary condition at x equals to xn by central difference at jth level, that is at un plus 1 j, this is nothing but un minus 1 j minus 2 delta x by alpha n beta n un j minus gamma n there. Similarly, since each of these time steps we can just increment it one by one, so that is why it can be written in the form of like j plus 1th level as un minus 1 j plus 1 here minus 2 delta x by alpha n beta n un j plus 1 minus gamma n. Since if we are just putting a fictitious boundary condition at the first boundary and along the last boundary here, then we can just find this boundary condition at each time step level to compute in a iterated manner or we can just update these values in a iterator manner if you will just go from one time steps to the next time steps there over. Also, if un plus 1j is known by this previous equation, that is like 10.7 here, but un plus 1j plus 1 is not known, then we can just move further. When there is a derivative boundary condition, that formula can be used for internal mesh points, also used for end points, that is I equals to 0 to n there itself. So, sometimes if you will just use the central difference approximation for these explicit formulas, that is like if I equals to 0, suppose we can just write this formula as u0j plus 1, this is r ui minus 1j plus 1 minus 2r u0j plus r u1j there itself. So, this means that if we are just solving this equation that has del u by del t, this equals to del square u by del x square here. Obviously, we will have this explicit scheme, or in the next step calculation, if you just see this molecule is formed in the form of like so this is the value which is to be computed, and this is the value you have to consider here for the computation of this point's value. And if you just approximate this value at this point here, so it should needed 2 more points there itself. So, that is why if we are just computing this value at u0 j plus 1, suppose this is the boundary here, then this requires this point and this point here. So, that is why it is just written as r of ui minus 1j plus 1 minus 2r u0j plus r u1j here. And directly you can just write this as I equals to 0 here, I equals to minus 1 here, I equals to 1 here, I equals to 2 here. And this value of u of minus 1j is substituted from this previous calculation, that is from 10.5, if you just see here, that is defined as u1j plus u0j relationship. So, we can just use this relationship as in the form of here, that is u0j and u1j is known to us, and u of minus 1j it can be directly substituted, and we can have the coefficients in the form of u0j and u1j there. So, directly we can just say that u0 of j plus 1, this can be involved only the terms that is 0j and 1j there. And similarly for the other end, like at the last boundary, if you will just go for this computation un j plus 1, this can be written in the form of r of un minus 1j plus 1 minus 2r unj plus r un plus 1j. Last boundary, if you will just see here, so this will just form these molecules, like if this is the last boundary here. So, this will just consider these points and this point for this calculation of explicit scheme there. So, this point it is not known to us, and this point is considered from this fictitious boundary conditions. And this value can be computed from this our earlier computation central difference scheme there itself, which can be expressed in the form of like un minus 1j and unj. And directly we can just establish this relationship between these 2 points with this one, and which can be replaced by these 2 points, and combinedly form of n minus 1 and n point, we can just obtain the value of unj plus 1 there. Since more than like 2 points it is involved for the calculation, so order of accuracy is more than the first order like forward difference scheme or backward difference scheme for this method here. And if Crank-Nicholson scheme is used, then for I equals to 0, we can just consider this one as minus r ui minus 1 j plus 1 plus 2 into 1 plus r u0 j plus 1 minus r u1 j plus 1, this equals to r u minus 1 j plus 2 into 1 minus r u0 j u1 j here. And this is minus 1 here and this minus 1 here. So, these are these fictitious boundary conditions we have just considered here. And these values can be replaced by using our earlier formations, so which we have just put, that as u of minus 1 j plus 1 and u of minus 1 j there itself. Since j plus 1 and j are the time step variation there, and these coefficients minus 1 remain fixed there, so along these boundaries. So, if you will just use this equation for this unknowns of computations like u0 j plus 1 and u1 j plus 1, so we can just obtain the values there. Similarly, for I equals to n, if we can just go for this Crank-Nicolson scheme, then we can just obtain this fictitious boundary as in the form of n plus 1 j plus 1 here, and this last one, this will also give you n plus 1 j here. So these boundary conditions can be replaced in terms of like nj and n minus 1 j by considering this earlier definition of boundaries, and we can get the equations with unknowns like un minus 1 j plus 1 and un j plus 1. So hence we will have like n minus 1 equations with the internal mesh points, and we can just form a set of n plus 1 equation with n plus 1 unknowns, that is in the form of like uij plus 1. And these equations form a tridiagonal system which can be solved by Gaussian elimination method. So for the heat conduction equation, if you just consider this equation, that is nothing but del u by del t equals to del square u by del x square, where x lies between x0 equals to 0 and xn equals to 0.5 here for t greater than 0, and the initial condition is given as u of x0 equals to 4x square. So we can just formulate this domain as in the form of like x equals to 0 here, x equals to 0.5, and we can just discretize this domain, that is in the order like if you will just see here x equals to 0.25, 2 equal parts, since the question is asked here, that is 0 to 0.5 into 2 equal parts. So we can just write this one as a 0.25 here. So final point is 0.5. So the problem statement is that for the heat conduction equation del u by del t equals to del square u by del x square, x lies between 0 to 0.5, t greater than 0, with boundary conditions u of 0 t equals to 0, del u by del x equals to 4 at x equals to 0.5, and initial conditions u of x0 equals to 4x square. And we have to solve this problem by dividing this interval 0 to 0.5 by 2 equal parts by explicit method. For t equals to 0, 0.025 and 0.200 here. So approximate these derivative conditions by backward difference, it is given us. So we can just write del x equals to 0.25, del t equals to 0.025 here. If you just see here time increment, it is just given like first time it will just given as a 0 here, then 0.025, then it will added once more, that is a 0.05. So up to 0.2 we have to move. So this is nothing but t starting value is 0 here, ending value is 0.200 incremented by 0.025. And for this scheme, for del t equals to 0.025, we can just obtain the r value as a del t by del x square, that is nothing but 0.025 by 0.0625, this is 0.4 here. So if you will just use explicit method, then we can just write this formulation as in the form of uij plus 1. Since the molecule can be formed in the form of like this is the unknown here, so these three values it can just use to get this next approximated value. So uij plus 1, it can be written as like r u minus 1 j plus 1 minus 2 r uij plus r u by I plus 1 j here. So next time step, if you just see here j plus 1th label I have just written here. So this is just taking I minus 1 j, then uij, then ui plus 1 j here. And if you just use this r equals to del t by del x square here, so this coefficients can be written in the form of 0.4. So since r is written or involved with these two terms here, so ui minus 1 j plus ui plus 1 j plus 0.2 into uij here. So for I equals to 1, u1 j plus 1, this can be written as 0.4 u2 j plus 0.2 u1 j here. And for I equals to 2, approximating boundary condition by backward difference, if you will just approximate, then we can just write u2 j plus 1 minus u1 j plus 1 divided by 0.25, this equals to 4 here. So directly if you will just put this value, we can just obtain this one u2 j plus 1 as u1 j plus 1 plus 1 here. And if you will just go for this computation at all other steps, so we can just obtain the values are in this form here, that is t equals to 0, then 0.25, 0.5, then 0.075, then 0.1, then 0.125, 0.150, 0.175. So you will have like 3 steps we are just computing here, that is at x equals to x0, that is nothing but 0 here, and xn equals to 0.5 we are just considering. So that's why we can just consider this one as x2 here, and x1 value is just taking as 0.25 here. So that's why this is very easy to compute in explicit approach, since 3 different points it is already asked to find it out. So if you will just go for this problem by replacing the boundary condition at x equals to 0.5 by central difference scheme here, then we can just write for I equals to 1 the scheme as u of 1j plus 1, this equals to 0.4 u2j plus 0.2 u1j here. And by central difference approximation, we have to consider a fictitious point there. So especially this fictitious point, since the last boundary point is a 2 here, so we have just considered u3j minus u1j, this by 0.25 as 4 here, and u3j this can be written as u1j plus 1 there. So if you just use explicitly this formula for I equals to 2 here, we can just obtain this one as u2j plus 1, this is nothing but 0.4 u1j plus u3j plus 0.2 into u2j, and u2j plus 1 this can be written as 0.4 to u1j plus 1 plus 0.2 into u2j. So if all of these points, if you just use these values, then simultaneously we can just obtain these values, that is just figured in this tabular form here. And if we will just use this schemes for Crank-Nicolson scheme with delta equals to 0.1, the derivative boundary condition is approximated by a backward difference scheme here. So del x can be written as 0.25, since the domain is defined in the form of like 0, then 0.5, then 0.25 here. So we can just write this formulation in terms of Crank-Nicolson scheme as minus r ui minus 1j plus 1 plus 2 into 1 plus r uij plus 1 minus r ui plus 1j plus 1, this equals to r ui minus 1j plus 2 into 1 minus r uij plus r ui plus 1j. And if you just put the coefficient r here, that is in the form of 1.6 here, then we can just write this formulation in this form here. And if we will just separate this unknown terms in the left hand side and the known terms in the right hand side, we can just write this equation as minus 4 ui minus 1 j plus 1 plus ui plus 1 j plus 1 plus 13 ui j plus 1, this equals to 4 into ui minus 1 j plus ui plus 1 j minus 3 ui j. If you will just see here, j plus 1 is the unknown level and jth is the known level here. For I equals to 1, if you will just put here, so u0 j plus 1, this is nothing but the boundary values, and u2 j plus 1, and then 13 u1 j plus 1, this equals to 4 u0 j plus u2 j minus 3 u1 j here. And this implies that we can just replace this one as in the form of like 13 u1 j plus 1 minus 4 u2 j plus 1, this equals to minus 3 u1 j plus 4 u2 j. So finally, if you just approximate this boundary condition by a backward difference approach, we can just write u2 j plus 1 minus u1 j plus 1 by 0.25, this equals to 4 here. So u2 j plus 1, it can be written as a u1 j plus 1 plus 1 here. So from equation 2 and 3, we can just write 9 u1 j plus 1, this equals to 4 minus 3 u1 j plus 4 u2 j. And u1 j plus 1, this can be written as 1 by 9 into 4 into 1 plus 3 u2 j minus 3 u1 j. And for j equals to 0 here, suppose if we are just putting, then u11, it can be written as like 1 by 9 4 into 1 plus 3 u2 0 and minus 3 u1 0 here. So we can just write in the final form as 1 by 9 16 plus 9 u1 j there itself. So if you will just go for this further computation, so especially we are just getting this derivative boundary condition just produces us like 0.000 here. So 0.0, so these are the initial conditions, it is just provided to us. Since at t equals to 0, we are just considering these values. So at 1 0.100 we are just finding this values as 0.0, 0.8944 and 1.894, but in explicit scheme especially we are just getting this one in the form of 0.8812 here. So it is too less compared to, or it is less compared to the Crank-Nicholson scheme. And if we are just putting here as t equals to 0.20 here, 200, then we are just obtaining this boundary values as 0, since it is just given in the problem, that is given initially. But along the last boundary, if you just see, so this has just taken the value 1.9883 here, and if it is updated with this initial domain value, it is just producing 0.9883. So, but the explicit scheme we are just obtaining this value as 0.9846 there. So, if you will just take these differences, so then we can just find that this difference is very minute there compared to the earlier one. So, this means that when we are just moving towards this higher time steps or towards this like more iterations, then we are just obtaining this closer values of the accurate solution. This means that either you are just using explicit scheme or implicit scheme, but if you are just getting this more iterations, or if you are just moving to higher time steps, then you are just approaching close towards the true solution there. Thank you for listening this lecture.